Welcome to the video on substitution nucleophilic bimolecular. So this video we're going to be talking about SN2. So for all substitution reactions, we have a nucleophile that reacts with an alkyl halide substrate, and we got our product where the nucleophile has replaced the leaving group. The nucleophile is a Lewis base or an electron pair donor. And typically for SN2, we are going to want it to be negatively charged. It can be neutral, but for this situation for SN2, we want it to be negatively charged. And so a nucleophile is very often referred to as a strong base. The leaving group, on the other hand, needs to leave. So that needs to be stable on its own. So that is a species that takes that pair of electrons from the alkyl halide and leaves. A very good leaving group is the halogens, like chlorine, bromine, and iodine. So a typical substitution reaction would look like this, where we have an alkyl halide and we have a nucleophile, and that nucleophile then will react with the halide to give us our product, which is the substitution product, where the OH replaced the Br on the substrate, and then we have our leaving group, which needs to be stable on its own as it leaves. The first thing we have to talk about is our substrate. And so if we have a carbon that has 3 small groups on it, typically it's going to be all 3 hydrogens. One of those could be a carbon, and that would be a primary. So a methyl and or a primary with a good leaving group. And so this is going to be a great substrate for SN2. And then if we have our nucleophile coming in, and our nucleophile is going to be negatively charged for an SN2, we want it to be nice and strong. In a sense, it kind of gets that reaction going. So we have the 2 electrons, the lone pair, from the nucleophile, reaching out and forming a new sigma bond with that carbon, and then that carbon ends up having the bromine leave, because carbon can only have 4 bonds. So this is a concerted reaction where the attack of the nucleophile and the loss of the leaving group happen in the same step. So this is concerted, it happens in one step, and what we end up with is a transition state. No intermediate in this one, just a transition state. And that transition state happens where we have our bromine bond half broken and our OH bond half formed. And so this transition state is pentavalent because it has carbon that's coordinated with 5 things, but we know it can only have 4 bonds. So this bond right here is half formed, and this bond right here is half broken. And then if we look at our product, we still have carbon with the 3 hydrogens, but our nucleophile is now attached, and the leaving group is on its own. So for an SN2 reaction, we need a very strong nucleophile for this to happen. As a matter of fact, we want the nucleophile to be charged. We want a negative nucleophile for SN2. The leaving group needs to be a weak base, but as long as it is a weaker base than the strong nucleophile, we should be good to go. The rate of this reaction is equal to a rate constant times the concentration of the substrate times the concentration of the nucleophile. And that is because both the nucleophile and the substrate are involved in the rate limiting step, and in this case, the only step. And so because both the substrate and the nucleophile are involved in that first step, that only step, they are both also included in the rate expression. And so this is a second order reaction, and the concentration of the substrate and the concentration of the nucleophile are important in the rate expression. If we were going to draw an energy diagram for this reaction, we see our reactants here, which is our alkyl halide, and we have a single step to get to our alcohol product. So this is a concerted reaction that is one step. So our reactant here is our alkyl halide, and our product here is our alcohol, and that tippy top right there, that transition state, looks like that. Now, if we go back and talk about our substrate for a second, we want our substrate to be open and unhindered. And so in this case, we have 3 H's. Now, one of them could be a methyl, so it could be primary, or it could be methyl, we want the substrate to be unhindered and open. And the reason for that is our nucleophile comes in from the backside. So our nucleophile right here, our strong nucleophile, does backside attack as it attacks that carbon, and then the bromine leaves out the front. And so we end up having this nucleophile approaching from one side of the molecule and the leaving group leaving from the other side of the molecule. And that's called backside attack. And what that does is it gives us complete inversion of stereochemistry. So if this molecule right here was R, complete inversion would give us S. Complete inversion of stereochemistry, and that is because of the backside attack. Now, in terms of the solvent, for SN2, we are going to need our solvent to be polar aprotic. We need a dipole in that molecule so that all of these charged species can dissolve, but we don't need any protons that can be donated because we need that nucleophile left good and strong. We do not want that nucleophile to be stabilized in any way. Some good polar aprotic solvents that you may see are acetone, DMF, which is dimethylformamide, and DMSO, dimethyl sulfoxide, and acetonitrile. So I just wanted to show you real quick the summary sheet that I made for you. For SN2 reactions, our substrate needs to be methyl or primary. We need lots of room. It's a concerted mechanism shown here where we have nucleophilic attack and loss of a leaving group in the same step. Some good leaving groups are shown here. And again, it has all to do with basicity. So good leaving groups are going to be the weak bases. So iodine, bromine, chlorine, and then we can have this tosyl group here, and water will leave. Remember I said OH never leaves, but water can leave. Some bad leaving groups. Fluorine is not so good. OH minus, there's a alkoxide, right? And so negatively charged things that are not stabilized, that are conjugate bases that are not stabilized very well, are not going to be good leaving groups. So the mechanism is such that it is a single step and concerted, and it is second order. The substrate reactivities are going to be methyl is the most reactive, followed by primary, then secondary is a little bit, and then tertiary will not happen with SN2. The rate expression of this reaction is such that the rate constant times the concentration of the alkyl halide times the concentration of the nucleophile. Both are involved in that single step, so both concentrations matter in the rate expression. In our stereochemistry, because of the backside attack, we have complete inversion. So if we start with R, we end up with S. And this one shows a true example of a stereocenter. This is a secondary carbon, which again is not ideal in terms of substrate, but it can happen with a secondary. And this shows then complete inversion. The R goes to the S. Now, if we talk about the energy diagram here, shows that it's a single step, it's concerted, and the only thing we really have to worry about is that transition state, that very high energy situation where bonds are half broken and half formed. And that is shown here in the gray box. And so this just describes the different energy profiles looking at a methyl alkyl halide, a primary alkyl halide, and a secondary alkyl halide. So the activation energy increases as we have an increasing number of carbons on our substrate. For SN2, we need polar aprotic solvents. So it's compounds that have polarity, but do not have any proton that can be donated. Some very common examples of polar aprotic solvents are acetone, DMSO or dimethyl sulfoxide, DMF, which is dimethylformamide, HMPA, which is hexamethyl phosphoramide, and acetonitrile. These are very common polar aprotic solvents. This is what we need for SN2. Here are the ones that we're going to need for SN1, but we'll talk about those later. So I hope that helps you think about SN2. Just a quick recap from what we talked about in lecture. Good luck.